In this video, we're going to discuss sampling distributions, which is the final tool that we're going to need before we begin inferential statistics. So what is a sampling distribution? Well, the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. So again, this says that a sampling distribution is a distribution of a statistic. So let's recall what a statistic is. A statistic, if you'll remember, is a numerical summary of a sample. And that is as opposed to a parameter, which is the numerical summary of the entire population. So when we're talking about a statistic, we're talking about calculations such as X bar, S, and so on. Okay, so these are statistics. So a sampling distribution is going to be a distribution of these types of statistics. So we're going to look at actually two different types of sampling distributions. In this section, we're going to look at sampling distributions of the sample mean X bar, and in the next section, we're going to look at sampling distributions of a sample proportion, which we're going to call p hat. So the sampling distribution of the sample mean X bar is the probability distribution of all possible values of the random variable X bar computed from a sample of size n from a population with a mean mu and a standard deviation sigma. So what exactly does this mean? Well, suppose we had a population, and let's make the population small. Let's say we had a population that had 25 individuals in it. And suppose we were going to select samples of size 3 from that population. So lowercase n is going to equal 3. Well, then how many different samples would be possible? Well, we've learned how to do that. This would be a combination problem. So this would be the combination of 25 choosing 3 individuals at a time. So if I pull in my calculator, 25 choose 3, there would be 2,300 different samples possible. So 2,300 samples possible. Now, if we were to find every one of those 2,300 different samples and calculate a statistic on those samples, so for example, if we were to calculate the mean of each one of those samples, then the first sample that we would obtain would have a mean, which we'll call X bar sub 1. The 1 would just be mean that is the mean of the first sample. And then for the second sample, there would be an X bar. So that would be X bar sub 2. And for the third sample, there would be an X bar. And for the fourth sample, there would be an X bar. And so on until we got to the last sample, the 2,300th sample. And so it would have an X bar. So that would be potentially 2,300 different values. Now, if we were to arrange those different values into a relative frequency distribution, and if we were to construct, say, a histogram from that relative frequency distribution, then that would be a sampling distribution of the sample mean X bar. And so often we just call that an X bar distribution, a sampling distribution of the distribution X bar. So this is what a sampling distribution is, and it's very important for you to understand what we're talking about when we're talking about a sampling distribution. So let's look at an example of a sampling distribution problem. So suppose a population consists of the following 6 data values. So we have 8, 12, 12, 16, 20, and 28. We have 4 parts to this problem. Part 1, we want to compute the population mean. Part B, we want to use using samples of size n equals 2, we want to construct the sampling distribution of x bar. In Part C, we're going to compute the mean of the sampling distribution of x bar, which we will denote mu sub x bar. And then in Part D, we want to compare the results for parts A and C. So we want to compare the mean of the population with the mean of the sampling distribution of x bar. So to begin with, we need to find the mean of the population. So to find the mean of the population, we're just going to add up our 6 data values and divide by 6. So mu is going to equal 8 plus 12 plus 12 plus 16 plus 20 plus 28, and that's all going to get divided by 6 because there are 6 data values. So that gives us 96 when we add up our 6 data values divided by 6, and 96 divided by 6 is 16. So our population mean, the parameter for this population, mu, is 16. So that is our answer to Part A. In Part B, we want to construct the sampling distribution if we choose samples of size 2. So let's consider that on a separate sheet. So here I have rewritten our population of 6 data values. And so we're going to create a sampling distribution of all of the possible samples of size 2. So to begin with, let's figure out how many different samples would be possible, samples of size 2. Well, we have 6 items, and we're going to choose 2. So this will be a combination of 6 items, choosing 2 at a time. So that will be 15. There will be 15 different samples of size 2 from our population of 6. And so we're going to list all of the different samples that are possible. So we're literally just going to list out all of the different samples that are possible. So we're going to do this systematically. So I'm going to start by pairing 8 with each of the other values, then 12 with each of the other values, the other 12, and so on. Okay? So 8 could be paired with 12. 8 could be paired with the other 12. 8 could be paired with the 16. 8 could be paired with the 20. 8 could be paired with the 28. So I have paired 8 with the other 5 data values. Now 8 has been paired, so I don't need to pair 8 with anything else. But I do need to pair this 12 with the other 4. So I could have 12, the first 12, paired with the other 12. 12 paired with the 16, 12 paired with the 20, and 12 paired with 28. So I'm pairing this 12 with the other 4 data values. Again, I'm not doing 8 because we had already paired 8 with 12. Now I'm going to pair the other 12 with the remaining 3 data values. So 12 is going to be paired with 16, 12 is going to be paired with 20, and 12 is going to be paired with 28. So again, pairing this other 12 with the 3 other values, not pairing with 8 or with this 12 because we've already done that. Now I can pair 16 with 20 and 28. So 16 paired with 20, 16 paired with 28, and last but not least, pair 20 with 28. So 20 paired with 28. So there are 15 different samples of size 2, and this literally gives us the 15 different samples that are possible. So we're going to calculate the mean for each one of those samples. So we're going to calculate x bar for each one of these samples. So I'm just going to average, like to begin with here, 8 and 12. Well, 8 plus 12 is 20. And 20 divided by 2 is 10. So that first sample gives us an x bar of 10. For our second sample, 8 plus 12 is 20, and 20 divided by 2 is 10 again. So we got 10 for the x bar of the second sample. Third sample, 8 plus 16 is 24, and 24 divided by 2 is 12. 8 plus 20 is 28, divided by 2 is 14. 8 plus 28 is 36, and 36 divided by 2 is 18. 12 plus 12 is 24, and 24 divided by 2 is 12. 12 plus 16 is 28, and 28 divided by 2 is 14. 12 plus 20 is 32, and 32 divided by 2 is 16. 12 plus 28 is 40, and 40 divided by 2 is 20. 12 plus 16 is 28, and 28 divided by 2 is 14. 12 plus 20 is 32, and 32 divided by 2 is 16. 12 plus 28 is 40. 40 divided by 2 is 20. 16 plus 20 is 36, and 36 divided by 2 is 18. 16 plus 28 is 44, and 44 divided by 2 is 22. And last but not least, 20 plus 28 is 48, and 48 divided by 2 is 24. So again, these are the 15 different samples that are possible, and these are the 15 X bars that we obtained from those 15 samples that are possible. So now we want to create a sampling distribution. So we want to create our sampling distribution. So a sampling distribution is a probability distribution of the different values of the statistics. In this case, our statistic is X bar. So I'm just going to rearrange this into a probability distribution. So I'm going to make X bar, and I'm going to find the probability of each of the possible X bars. Okay? So the first thing I'm going to do is list all of the different X bars that were possible. So I'm going to list the unique X bars that we obtained. So we obtained 10 for an X bar, we obtained 12 for an X bar, 14 for an X bar, 16 for an X bar, 18 for an X bar, 20 for an X bar, 22 for an X bar, and 24 for an X bar. These were the different values that we obtained for our X bar from our sample. And so we want to, again, make this into a probability distribution, which is really a relative frequency distribution. So if I randomly selected 2 data values from this population of 6 data values, what's the probability I would get an X bar of 10? Well, there were 2 different ways that I could get a 10 out of the 15 different X bars that were possible. So that probability of getting an X bar that equals 10 would be 2 out of 15. What about getting X bar of 12? Well, there was a 12 here and a 12 here. So there were 2 different ways of getting 12 out of 15. So the probability of getting an X bar of 12 is also 2 out of 15. Now 14. There's 1, 2, 3 different ways that we got a mean of 14. So the probability of getting X bar equals 14 is 3 out of 15. 16, there's 2 different ways. So the probability is 2 out of 15. 18, we could get 18 here or here. So again, 2 different ways. So 2 out of 15. 20, there we could get a 20 here and a 20 here. So again, 2 out of 15. 22, there's only one way of getting 22, so the probability of getting 22 is 1 out of 15, and in the same way, the probability of getting 24 is 1 out of 15. So here we have constructed our sampling distribution using these 6 data values for our population and choosing samples of size 2. Now in part C, we want to calculate the mean of this sampling distribution. So again, we're going to call that mu sub x bar. Well, remember, to find the mean of a discrete probability distribution, which this is, we take each data value times the probability and add those all up. That gives us the mean of our discrete probability distribution, which again, this is. So this is what we're going to do. I'm going to take 10 times the probability, 12 times the probability, 14 times the probability, add that up, and that's going to give me the mean. So I'm going to write that down here. The mean of our x bar distribution is going to equal 10, that was one outcome, times the probability of getting 10 as the mean, which is 2/15, plus 12 times the probability of getting 12, which is 2/15, plus 14 times the probability, which is 3/15, plus 16 times the probability, 2/15, plus 18 times the probability, 2/15, plus 20 times the probability, 2/15. I'm going to come down here, plus 22 times the probability, which is 1/15, plus 24 times the probability, which is 1/15. If we do this calculation, we're going to get 10 times 2/15 would be 20/15. 12 times 2/15 would be 24/15. 14 times 3/15 will be 42/15. 16 times 2/15 will be 32/15. 18 times 2/15 will be 36/15. 20 times 2/15 will be 40/15. 22 times 1/15 will be 22/15. And 24 times 1/15 will be 24/15. So if we add up 20 plus 24 plus 42 plus 32 plus 36 plus 40 plus 22 plus 24, that gives us 240 over 15. And 240 divided by 15 is 16. So when we found all of the possible means and put that into a sampling distribution, when we find the mean of the sampling distribution, we get 16. Now, in Part D, we're supposed to compare the results of Part A and Part C. Well, in Part A, we got a mean of 16, and in Part C, we got a mean of 16. So how do these results compare? They are equal. In other words, we found that the mean of the population equaled the mean of the x-bar distribution. And we're going to see in the next video that this is always true.